Welcome to Module 9. Today we are going to build your very first machine learning model from start to finish. I promise that by the end of this video, you will have personally trained and used a genuine ML model. In the last module, we set up our development environment with Colab, Python, and the necessary libraries. Now we put that toolkit to work on a real dataset. We will go through 5 steps: loading the data, exploring it, preparing it for training, building and evaluating the model, and finally, using it to make predictions. Let's start with part 1. Choosing and loading a dataset. Every real-world machine learning project begins with the data. We'll be using one of the most famous datasets in history to get you started. Why choose this specific dataset for your first project? Because it is small, clean, and well understood. It allows you to master the machine learning workflow without getting distracted by the complexities of messy, raw data, which we discussed in Module 7. This is the Iris dataset. It dates back to 1936 and contains 150 flowers, each measured across 4 features: sepal length, sepal width, petal length, and petal width in centimeters. The goal is to predict the flower's species from 3 options. Best of all, it is built right into Scikit-learn. Loading the data is straightforward. We import the dataset, load it, and convert it into a Pandas data frame for easy handling. Notice how iris.data maps to our features, and iris.target gives us the numeric labels. To get our first look, we simply print the head of our data frame. This follows the habit we built in Module 8, giving us a quick peek at the first 5 rows of our data. Part 2 is all about exploring the data. It is crucial to get to know exactly what you are working with before you start the training process. As we learned in Module 7, you should never blindly trust raw data. A quick sanity check now can save you from a lot of confusion later. Even if a dataset looks clean, it pays to explore it first. First, let's check the shape of our data. Using print, df shape confirms we have 150 rows and 5 columns, our 4 measurements plus the target species column. Next, we run df.describe. This single command gives us the count, mean, minimum, and maximum for our numeric columns, helping us quickly spot anything unusual. Finally, we visualize the data. By creating a scatter plot of petal length versus petal width, we can actually see the species starting to separate into distinct groups before we have even trained a single model. We also want to check the class balance. Printing the value counts shows us that we have exactly 50 flowers for each species. It's perfectly balanced, which is a rare treat compared to the messy, uneven real-world data we discussed in Module 7. Now for Part 3, preparing for training. We have 2 quick, essential steps to take before we can start teaching our machine learning model. Our first step is separating the features from the labels. We define X as our measurement features by dropping the species column, and we assign Y to the species label, which is what the model will learn to predict. Now we perform the train test split in code. By using test_size equals 0.2, we reserve 20% of the flowers purely for testing, exactly the 80/20th split we described in Module 5. Why split our data before doing anything else? We hold back 30 flowers entirely from the training process, so the model only learns from 120, ensuring we never mix training and testing, which would make the model look artificially perfect. This brings us to Part 4, training and evaluating. This is the moment. Everything we've covered in Modules 5, 6, and 8 comes together to build one real working model. We are going to use a decision tree. Remember the 4-line preview from Module 8? We are building that out for real now with the decision tree classifier, which is one of the most intuitive algorithms to start with. A decision tree makes predictions by asking a series of simple yes-no questions. For example, our model might ask, is the petal length less than or equal to 2.45 centimeters? This is the same if-then logic from Module 3, only learned from data instead of being handwritten. Training the model is simple. Behind the .fit method, the algorithm searches for the best questions to separate the species. This process is different from the neural networks in Module 6, but it follows the exact same .fit pattern we saw in Module 8. Now we make predictions on our test set. These 5 flowers were never seen during the training phase, which is why we performed that crucial split earlier. It's always a good idea to perform a quick gut check. By zipping our predictions with the actual labels, we can read them out loud, just like checking your own homework. Next, we calculate our accuracy score. Seeing a result of 96.67%, or 29 out of 30 flowers correctly identified, is a genuinely strong result from a model you just built yourself. Remember that accuracy can sometimes be misleading, as we noted in Module 5. However, since the Iris dataset is perfectly balanced, accuracy is a reliable signal here. It is still good practice to check if the model performs equally well across all species. Finally, we reach Part 5, predicting and reflecting. It's time to use our finished model on brand new, unseen data and step back to appreciate the full picture. We can feed entirely new measurements into the model to get a prediction. This is the essence of inference, a concept we introduced back in Module 6. The raw output is just a number representing the species, but with one more line of code, we can make it human-readable. In this case, our model successfully identified the flower as a Satoshi. Here is the entire pipeline in one place. Every step, from loading the data to getting the final prediction, is captured here in just 12 lines of clean, efficient Python code. To recap, we've walked through 6 clear steps: loading the data, exploring it, splitting it, training the model, evaluating it, and using it for inference. You've successfully navigated the core workflow of machine learning. We need to talk about a risk we highlighted in Module 5, overfitting. An unconstrained decision tree can become so complex that it essentially memorizes the training data. While 100% training accuracy looks great, it often means the model has simply memorized noise rather than learning the actual patterns, leading to poorer performance on new flowers. Now that you have the basic workflow, you can expand it easily. Try swapping the decision tree for other algorithms like k-neighbors or random forest. The best part? The .fit and .predict pattern stays exactly the same. You can also experiment with different built-in datasets like wine or digits, using this same process. Let's bust a few myths. First, a working model isn't the finish line. It requires ongoing monitoring. Second, you don't need thousands of lines of code. Our entire workflow was about a dozen lines. And third, not every dataset is as clean as Iris. Real-world data often requires the cleaning steps we covered in Module 7. It's time to check your knowledge. Please pause the video to answer these 4 questions. Which function splits our data? What does the first decision tree split achieve? What does .predict return? And finally, how can you improve this model? Take a moment, and then we will review the answers together. Let's review the answers. The train test split function comes from model selection. The first tree split perfectly separates the Satoshi species. The predict method returns a classification based on learned patterns, and you can improve performance by trying different algorithms or datasets, maintaining that consistent workflow we've practiced today. Here is a handy summary of the key vocabulary from this module. Feel free to pause and take a screenshot of these terms, as they are the building blocks you will continue to use throughout your machine learning journey. To recap our key takeaways, building an ML model is a logical, step-by-step process. We applied everything from modules 5 through 8 to build real code. Remember that while decision trees learn via yes-no questions, they still fit into the standard workflow. Finally, always be ready to iterate and improve on your initial results. Coming up next, in Module 10, we move into computer vision. We have spent this module training models on numeric data, but next, we will explore how machines learn to see by transforming images into data that a model can understand. Congratulations! You have officially built your first real machine learning model. This is a significant milestone in your journey. I look forward to seeing you in Module 10, where we will dive into the fascinating world of computer vision.